Welcome to the Deep Dive, the show where we break down the big architectural challenges in technology. Today, we are taking a deep dive into something that has, well, it's quietly become one of the biggest constraints on the entire modern internet, and that is energy consumption, specifically in server architecture.
It really is a complete paradigm shift. I mean, for the better part of 50 years, if you were designing a server, you cared about two things.
Speed and heat.
Exactly. Speed and heat.
Yeah.
You wanted the fastest possible processor, and your biggest worry was just getting rid of the peak heat it generated so it wouldn't, melt.
Right.
But now, the sheer cost of just keeping the lights on, the volume of electricity these things consume 24/7, has totally changed the game. Energy efficiency is now the dominant factor.
The dominant factor in what they call the total cost of ownership, or TCO.
That's the one.
And so the goal, the mission that researchers are now focused on, is this idea of energy proportionality. It sounds elegant, but as we're about to find out, it's incredibly hard to achieve.
The core mission is to design machines that consume energy in direct proportion to the amount of work they're actually doing. Simple to say, but
But our current servers are failing at it.
yeah.
Spectacularly. So let's start there. This concept of energy proportionality feels like it belongs in the mobile world, right? We all get why our phone needs to have good battery life. When did this become the #1 issue for massive grid-connected data centers?
It became critical the moment the scale of computing just exploded beyond what you could fit in a single room or a single server rack.
So it's a problem of scale.
It's entirely a problem of scale. We're talking about millions of servers now, and the economics of running them are frankly getting worse. The sources we're looking at are clear. Energy efficiency used to be all about battery life or managing those peak thermal moments.
Right, the don't melt the chip problem.
Exactly. But now it's a critical board-level issue for data center operations all over the world.
But I think most people hear that and assume, okay, the electricity bill is huge. But is that it? Is it really just about the raw cost of electricity?
That's what most people think. But it goes so much deeper. And this is really the first crucial insight for our deep dive today. That energy cost, it ripples through the entire data center ecosystem.
Right.
It's the dominant factor in that total cost of ownership, the TCO we mentioned. And TCO isn't one thing. It's a whole stack of expenses that are all dependent on energy.
Okay, so let's break down that stack. If I'm building a data center, what are the key pieces of TCO that are directly tied to how much power my servers are drawing?
You've got three major buckets. First, the obvious one, the server electricity bills, the raw operational costs, what you pay the utility company every month.
Simple enough.
Second, and this is one people often forget, is the cooling infrastructure costs. Every single watt of power your server consumes turns into heat.
And that heat has to go somewhere.
It has to be actively removed from the building. And that means running massive chiller plants, huge fans, pumps, all of which requires its own, substantial energy input.
So you're paying for electricity to run the server, and then you're paying for more electricity to get rid of the heat from the first batch of electricity.
Precisely. And then there's the third piece, the initial provisioning costs.
And that's the upfront capital, right? The cost of actually building the facility.
Exactly. We're talking about the power distribution units, the transformers, all the heavy-duty cabling, even the physical space itself. And the size and complexity of all that gear isn't determined by the average power you use.
It's determined by the peak power, what you might need on your busiest day.
Yes. The peak power the facility has to be prepared to deliver and then dissipate as heat. And here's the kicker, the crucial insight. Both the cooling costs and those big upfront provisioning costs are directly proportional to the average server energy consumption over time.
Okay, wait, walk me through that. It feels like a snowball effect.
It is a snowball effect. If you design a server that wastes, say, 50% of its power just sitting idle,
Which, as we'll see, is pretty typical.
frighteningly typical. You end up paying for that waste 3 separate times. You pay the utility for the wasted electricity. You pay again to run the chillers to cool the heat from that wasted electricity. And you pay it a third time, up front, to build a facility with massive infrastructure capable of supporting all that inefficiency in the first place.
So improving energy efficiency isn't just about saving a few bucks on the monthly bill. It shrinks your capital expenditure and your operational expenditure at the same time.
It's a force multiplier. It makes the entire economic model of the data center better. This is what elevates energy proportionality from just a nice technical goal to an absolute business imperative.
And this is all happening against a backdrop of relentless demand for more performance. The trend is always more, faster, bigger.
It's a treadmill. The long-term tech trends are clear. Higher performance requires more energy. So to stop the global energy footprint of computing from just, spiraling out of control, our energy efficiency has to improve at least as fast as our performance does.
It's like trying to run up a down escalator.
Or worse. If performance doubles but your efficiency only goes up by half, your total energy use still explodes. The only way off that escalator is a radical change in architecture, a shift towards this idea of proportionality.
So let's define that properly. If we were sitting down with a blank sheet of paper to design the perfect server, what does an energy proportional machine look like? What's the ideal?
The ideal, and it's a great analogy, is to make a server's power curve look like that of a simple industrial motor.
Okay.
If a motor is doing zero work, it's using zero power. It's off. If you run it at half its maximum load, it should use about half its maximum power. The ideal server would do the same. It would consume essentially zero power when it's fully idle,
Like truly off.
as close to zero as physically possible. And then, as you give it more work to do, the power consumption would scale up in a perfectly straight line, a linear curve, all the way to maximum utilization.
A one-to-one relationship between work done and energy spent.
That's the holy grail.
And if we could do that, if we could actually build this machine, what's the real-world impact? How big is the prize?
The potential game is, it's profound. The numbers suggest that truly energy proportional designs could double the efficiency of a typical server in real-world use.
Double.
Double. That means you could cut your data center operating costs in half overnight. That's a gain that is just, it's unheard of in this industry. People fight for a 5 or 10% improvement.
Yeah. Doubling efficiency sounds like a moonshot. But to understand how we get there, we have to first really dig into why we're failing so badly right now. And that means looking at what servers actually do all day.
And that's where we find the great mismatch. The fundamental problem is that server architecture is built on a completely wrong assumption about its own job, an assumption we inherited from the mobile world.
So we have to separate these two models, the way my phone works versus the way a server in a data center works.
They could not be more different. Let's start with the one we all know, the mobile model. Your phone, your laptop. It has what we call a bimodal usage pattern.
Bimodal meaning on or off.
Pretty much. You tap an app. For a very short burst of time, you need peak performance. The CPU ramps up, everything runs full blast because you, the user, are waiting.
Right, I don't want to see a loading spinner.
Nobody is. And then, almost immediately, the work is done. And the device becomes idle for a relatively long time, seconds, maybe minutes, while you read what's on the screen or put the phone away.
And that bimodal burst then wait pattern is what drove the whole design. Optimize for that peak burst, and then optimize for a really, really deep sleep mode to save battery during the long wait.
Exactly. You want to get to near zero energy consumption in those sleep states. Now contrast that with the server model. And our sources here are incredible. They're based on data from over 5,000 servers in a major internet company, tracked for 6 months.
So this isn't theory. This is real-world data. What is that data, what our sources call figure one? Tell us about the secret life of a server.
It tells us two truths that completely upend the mobile model. First, servers are rarely ever completely idle.
So no deep sleep.
Almost never. And second, they are seldom operating near their maximum utilization. They don't spend a lot of time running at 90 or 100% load.
Okay, so if they're not off, and they're not running at full tilt, where are they? Where do they live?
They live their entire lives in the middle. The vast majority of a server's operational time is spent between 10 and 50% of its maximum utilization.
10 to 50%.
That's the typical operating region. And that is the crucial insight. That's where all the money is being spent on electricity, and critically, that is where current server architecture is at its absolute worst in terms of efficiency.
The entire design needs to be re-optimized for that 10 to 50% band, not for 0% or 100%.
That's the mission.
But this feels inefficient. On the surface, why can't we just pack more work onto fewer machines and push them up to 90%? Wouldn't that be smarter?
It seems logical from a resource perspective, but it clashes with the fundamental principles of building a reliable internet service. You have to provision services with slack.
Psych, so headroom.
Headroom. That slack isn't waste, it's a requirement. Imagine if the average load on your web servers was always at 95%.
One news story breaks, one viral video, and you're down.
You're instantly saturated, any minor traffic fluctuation, any internal problem like a single machine failing or needing maintenance, and you can't handle the load. Your service slows to a crawl, you start dropping user requests, and you violate your service level agreements, your SLAs.
The promises you made to your customers about uptime and responsiveness.
Exactly. So you deliberately over-provision. You build in that buffer to handle the unexpected peaks. But the direct consequence of ensuring that reliability is that the average utilization sits low, right in that 10 to 50% zone.
It's the cost of stability.
It's the cost of stability. And there's another architectural reason that makes true idleness basically impossible, and that's distributed data.
This is a huge one. The way modern systems are built prevents us from turning things off.
It's probably the biggest barrier. Think about a system like the Google file system, which is what our sources reference. The whole design philosophy is to eliminate single points of failure.
Right.
You do that by spreading user data across thousands of different machines. Your photos are on one disk. They're chopped up and replicated across many. This gives you fault tolerance and high availability.
Because if one machine goes down, my data still exists on 9 others. I can still get to it.
Correct. But look at the architectural consequence of that choice. To ensure that you can always get to the data instantly, all of those servers must remain available and responsive, even when overall traffic is low.
You can't just power down a server, because a user query might need the specific piece of data that happens to be stored on that machine.
You can't. That would introduce a massive delay while you wake that machine up. So true idleness, a deep sleep state, is functionally impossible because of the need for low latency data access.
That's not just user requests, right?
Yeah.
I assume these servers are constantly chattering among themselves.
All the time. They're constantly doing small background tasks, health checks, data synchronization, garbage collection. It's a low hum of activity that never, ever stops.
So this continuous low-level hum is exactly why all the energy-saving tricks from the mobile world, these inactive power modes, are completely useless for servers.
They're worse than useless. They're actively harmful because of the enormous penalty barrier to using them.
The penalty. Let's dig into that, because the number in the source material is, frankly, shocking. It says a disk drive in a spun-down deep sleep state can have a wake-up latency 1,000 times higher than its normal access time.
1,000 times. And it helps to understand the physics of why that is. A traditional spinning hard drive, to go into deep sleep, has to physically stop the platters from spinning. They spin down from maybe 7,200 RPM to 0.
And getting them back up to speed isn't instant.
It's pure physics. You have to overcome inertia. It takes a significant amount of energy, a big power spike, just to get that mass spinning again. But more importantly, it takes time. Several seconds.
And in a distributed system that's trying to answer a web request in milliseconds, several seconds is an eternity. It's a system failure.
It is. The system would time out. And it's not just the spin-up time. The drive also has to wait for everything to stabilize thermally and mechanically before the read-write heads can safely and reliably access the data. That entire cycle can take minutes, not milliseconds.
So you can only use a mode like that if, with absolute certainty that the drive won't be needed for several minutes.
Which our workload data shows almost never happens in a busy data center.
So we've taken a system designed for a bimodal on or off world and tried to apply it to a world that lives perpetually in this dimly lit middle ground.
A perfect summary. The architecture is a mismatch for the workload, and the waste that results from that mismatch is phenomenal.
So let's quantify that phenomenal waste. The data is all there in the sources. When we look at Figure 2, which charts power use against utilization for a typical server? What's the first thing that jumps out?
The idle power draw, the baseline, it's shocking. A modern, supposedly energy-efficient server, when it's doing virtually no work, when it's sitting idle, is consuming about half of its full power.
50%, just to be turned on.
50% just to be on. And if it's an older server or one where less attention was paid to efficiency, that number can be even higher.
And that 50% idle cost is a boat anchor on the system's overall efficiency. Because if we define efficiency as, work done divided by power consumed,
then your efficiency only peaks right at 100% utilization, and the drop-off from that peak is incredibly steep.
a cliff.
It's an efficiency cliff. And now look at where servers spend most of their time, that 20 to 30% utilization range we talked about. In that zone, the actual energy efficiency of the system has fallen to less than half of what it is at peak performance.
Let me make sure I'm getting the math on that right, because it's brutal. I'm running a server that's using, say, 60% of its max power, but it's only delivering 25% of its max performance.
It's about right.
We are paying a premium operational price for a fraction of the work.
Yeah.
That gap is just pure waste. Wasted electricity, wasted cooling, wasted infrastructure.
It is the cost of the mismatch. The server is designed to be efficient at a workload it almost never sees, and it's incredibly inefficient at the workload it runs all day, every day. So to fix this, we have to find out where that 50% idle power is actually going.
Right. Who are the culprits?
For a long time, everyone just pointed the finger at the CPU. I mean, it's the brain, it's complex, it runs hot, it had to be the problem.
Seemed like a safe bet.
It was. But when you actually break down the power consumption component by component, that assumption turns out to be wrong, or at least outdated.
So Figure 3 in our sources does exactly that. It compares 2 generations of Google servers and shows the power breakdown. CPU, memory, disks. What's the big trend when you look at peak power usage?
The big trend is the CPU's diminishing role in the total power budget. It no longer dominates. And that's actually a huge success story for CPU designers. They've been incredibly aggressive about adding energy-saving features for the last decade.
Things like multiprocessing, power scaling.
Exactly. They've done a surprisingly good job of making the CPU's power draw more proportional to its load.
Okay, so if the CPU isn't the main villain anymore, where is all that idle power coming from? What happens when we look at that server when it's sitting idle?
That's the smoking gun. When that 2007 server is idle, the CPU's slice of the power pie gets even smaller. It scales down its power consumption pretty well. This tells us that the CPU is actually the most proportional component in the whole box.
Wow.
The bulk of that idle power, that 50% of peak we're wasting, is being burned by everything else.
The non-CPU components.
To non-CPU components. The conclusion for any system architect is unavoidable. To achieve energy proportionality, we have to fundamentally redesign the rest of the system, specifically the memory and the disk subsystems.
That's where the new frontier is.
Absolutely. The problem isn't the brain anymore. It's the supporting cast, the DRAM, the storage, and increasingly the networking hardware. They are fundamentally non-proportional, and they're eating up more and more of the system's energy budget. They are the new targets.
Okay, so the CPU is a role model. If we want memory and storage to be as efficient as a modern processor, we need them to adopt the features that the CPU designers have already perfected. The sources point to 2 key architectural requirements.
2 non-negotiable features. And the first one is having a wide dynamic power range.
Dynamic power range, that's the difference between your peak power draw and your minimum power draw while you're still active, right?
Exactly. It's the gap between your maximum power and your active idle power. You need that gap to be as wide as possible.
So what's the benchmark? How wide is the CPU's range?
A modern server processor can achieve a dynamic range of more than 70%. That means when its activity is very low, it can drop its power consumption to less than a third of its peak.
Which is a huge drop.
It's massive, and the CPUs in your phone are even better. They can often get down to 10% or less of their peak power without going into a deep sleep. So that 70% range is our target.
Now let's compare that to the components that are dragging the system down. How do they stack up?
They don't. It's not even close. Let's take main memory, DRAM. It has a dynamic range of less than 50%.
So even when the system is totally idle, the RAM is still burning more than half the power it would at peak load.
More than half. Disk drives are even worse. They have about a 25% dynamic range when they're active and spinning.
And networking gear is the worst of all.
By far. Networking switches often show a dynamic range of only 15%. Your server could be doing nothing, just waiting for a request, and the switch port it's connected to is still drawing 85% of its peak power just to keep the link up.
Let's pause on the DRAM for a second, because that seems strange. If you're not reading or writing data, why can't it just power down significantly? What's the physical limitation?
The limitation is the D in DRAM dynamic. The data is stored in millions of tiny capacitors. And capacitors, by their nature, leak charge over time.
So they forget.
They forget. To prevent data loss, the memory controller has to constantly go through and recharge or refresh every single one of those capacitors thousands of times per second. And that has to happen whether the CPU is actively using the data or not.
So there's this constant baseline level of activity just to maintain the data's integrity.
Exactly. And that refresh activity creates a very high power floor. It makes DRAM fundamentally non-proportional. The only way to fix it is to make the refresh cycles themselves proportional to memory access, which is an incredibly hard problem.
So the big design challenge for manufacturers is to re-engineer these components, to just crush that minimum power floor downwards and get them closer to that 90% dynamic range.
That's job number 1. But there's a second requirement that's maybe even more important, and that's adopting active low-power modes.
Active modes. This is the key to solving that 1,000 times latency penalty we talked about with disks.
This is the entire solution. We have to draw a bright line between inactive modes and active modes.
Inactive is deep sleep. Spin down the disk, shut everything off.
Right. Saves the most power, but you pay that catastrophic multi-second wake-up penalty. Active low-power modes, on the other hand, let the component stay on and ready, just in a lower performance, lower power state.
And there's no big software visible transition needed. It just works.
It just works. The component stays awake and operational.
And the CPU is the master of this with something called dynamic voltage and frequency scaling, or DVFS. Can you break that down for us? Why is that so effective?
Well, DVFS exploits a fundamental relationship in physics. The power a chip consumes is roughly proportional to its capacitance times its voltage squared times its frequency. P equals CV squared F.
And the voltage squared part is the magic lever.
That's the magic lever. If you reduce the operating frequency by, say, 20%, you can also reduce the operating voltage.
Right.
But because power is proportional to the square of the voltage, a 20% voltage drop gives you a nearly 36% drop in power consumption.
So you get way more power savings than the performance you give up.
A quadratic savings. The CPU can run a little slower, but at vastly lower power, without ever needing to shut down, lose its state, or pay a wake-up penalty. It's always active, always ready to ramp back up instantly if the load increases.
But nothing else in the box can do this. Mainstream memory and disks only give you the one option: fully on or fully inactive deep sleep.
And that's the core of the problem. If a server has a quiet moment that lasts for 50 milliseconds, the disk can't spin down because it would take 2 seconds to spin back up. You need active modes. You need memory that can slow down its refresh rate if it's not being accessed frequently.
And for storage, something like an SSD that can throttle its internal controller speed, but still be ready to respond in microseconds, not seconds.
Precisely. And the huge advantage of these active modes is how they handle overhead. It's all about amortization.
Yeah.
Because the transitions between active modes are so fast and low energy, the system can stay in these low power states for as long as the workload stays low. The cost of switching is negligible.
Which maps perfectly to that server workload profile we keep coming back to.
It's a perfect match. Those long periods of low activity in the 10 to 50% range are way more common than moments of complete 100% idleness. So the tiny overhead of shifting between active power states gets amortized or spread out over a much longer time. It's far more effective than paying the huge overhead of going in and out of those disastrous inactive modes.
It seems like if the hardware just did this automatically, you would need all this complex software trying to predict the future, trying to guess if it's safe to put a disk to sleep.
You're taking the problem out of the software layer and solving it in the silicon where it belongs.
Yeah.
You make the system inherently automatically proportional, and that is the architectural revolution we need.
It's a massive engineering challenge for the component makers. But the sources also ran simulations to show what the payoff would be. They modeled what happens if we actually build this ideal proportional server.
Yes, and that data from Figure 4 is the carrot at the end of the stick. The simulation models a server where every component works together to achieve a 90% dynamic power range.
So instead of that catastrophic 50% idle power, this ideal server only consumes 10% of its peak power when it's doing nothing.
That's the goal.
So what does that do to the bottom line? Let's start with the operational costs, the electricity bill.
The numbers are staggering. In terms of just raw energy usage, a data center full of these servers could cut its total energy consumption by 1/2.
A 50% saving.
50%. That kind of saving justifies any R&D investment you can imagine. It completely changes the economics of the cloud.
But let's go back to our TCO stack. It's not just the running costs. What does this do for the upfront capital costs, the provisioning?
This is where it gets even better. Because the peak power of the whole facility is lower, the simulations predict that these proportional servers would lower the required peak power capacity at the data center level by more than 30%.
A 30% reduction in peak power. That's huge. That means your transformers can be smaller, your power distribution can be less complex, your cooling systems don't have to be as massive.
It means you can build a data center for 30% less money, or you can fit 30% more computing into the building you already have. The return on investment for the capital is accelerated enormously. This is the point where CFOs start paying very close attention.
And you get all of this without sacrificing any peak performance.
Yeah.
The top speed is the same, the gains all come from fixing the inefficiency at the low end.
Exactly. And when you look at the efficiency profile of this simulated server, that efficiency cliff we talked about is just gone.
Replaced by what? A gentle slope?
It's more like a high plateau. The ideal server maintains over 80% of its peak efficiency all the way down to 30% utilization. Even at a very low 10% utilization, it's still over 50% efficient.
That's a night and day difference from today's servers, where the efficiency has already fallen off a cliff by the time you hit 20% utilization.
You move from a terrible mismatch to a near-perfect alignment between the architecture and the actual work it's being asked to do.
And there's another benefit here beyond the financials, which is simplicity. If the hardware becomes proportional, what does that do to all the complex power management software running on these systems?
A lot of it could just go away. So much of today's power management software is, well, it's a complicated, brittle workaround. It's software trying to solve what is fundamentally a hardware problem.
Right.
If the hardware components scaled their own power automatically and instantly, you could simplify or maybe even completely eliminate that entire software layer. The system administrator's job then just becomes about managing utilization, making sure the right number of jobs are on the machine, not trying to micromanage its power state.
That's a massive reduction in complexity and a massive reduction in things that can go wrong.
It is. But to get the industry to actually make this change, one last thing has to happen. The way we measure and benchmark efficiency needs to evolve.
Because right now, the benchmarks are focused on the wrong thing.
They're almost exclusively focused on peak performance efficiency. You run the server at 100% load and measure its performance per watt.
Which, as we've established, is a state the server almost never operates in. So it gives you a misleadingly rosy picture of its efficiency.
Totally misleading. So the call to action from the researchers is for benchmark creators to start reporting measurements at non-peak activity levels. We need standardized tests that measure efficiency across that critical 10 to 50% utilization range.
Because if the benchmarks don't reward efficiency in the typical operating zone, then designers won't be incentivized to build for it.
You get what you measure. We need to start measuring what actually matters to the people running these massive data centers, not just what's easy to test on a lab bench. The rules of the game have to reflect reality.
So to wrap this all up,
I think to synthesize this deep dive, the core problem is pretty clear. Our servers, especially their memory and storage, are fundamentally non-proportional. They waste about half their power in the low-activity state where they spend most of their lives.
a massive architectural mismatch.
A massive mismatch. And the solution is, in concept, simple. We have to give every component the same abilities that the CPU already has, that wide dynamic power range, and those active low-power modes that avoid the catastrophic penalties of deep sleep.
And if we do that, the reward isn't just about being green. It's a complete economic overhaul of the data center, doubling efficiency, cutting capital costs by a third, and making the whole system simpler to manage.
It's really the only sustainable path forward for the Internet's infrastructure. It is the future economic architecture.
So as we always do, we'll leave you with the final provocative thought to chew on. This one builds on that TCO stack we talked about at the beginning. Let's imagine the industry succeeds. We achieve near-perfect energy proportionality. Servers use almost no power when idle and scale up perfectly. The battle over operational electricity costs is, for the most part, won. If that happens, what's the next big hidden cost in the data center TCO that designers will go after? Think beyond the monthly power bill. Think about the energy and cost embedded in building the facility and manufacturing the hardware in the first place. What happens when the cost of running the machine is finally dwarfed by the cost of creating it? Something for you to explore on your own. Thank you for joining us for this deep dive into the architecture of energy proportionality. We'll see you next time.